Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to walk you through a demonstration of how to apply Gauss's law to find electric fields. So what I want to focus on is over here. So imagine we have a total charge Q uniformly distributed into a spherical volume of radius r. So again, this is kind of a 3D problem here. And just some observations here before we move along. If I were to put a positive charge right at the center of this thing, and you'll notice there's, if I look at how much charge is here, if I go directly across, same amount of charge. Or if I look at charge here, I go directly across, same charge. It's a very symmetrical problem. So one thing to notice is that the electric field at the center of that must be zero, because there'd be no net force on any charge put at the center. However, imagine I put a positive charge maybe right here. You'll notice that there's a bunch of charge here creating a field at this location that points to the right. So there definitely is an electric field at the outer surface. Now imagine that my point here, is somewhere in the middle, like right about here. And imagine putting a positive test charge here. And think about the symmetry. In this region here, really close, the problem's symmetrical. But as I get further out, you'll notice that there's some charge over here that doesn't have a counterpart over here. Therefore, there must be an electric field in the interior as well. So just some general observations here. We know that the electric field at the center is zero. We know that the electric field vector, we know that the electric field at the outer surface is some value that we don't know yet. And we know that there also has to be an electric field within the interior. So now what we're going to do is we're going to try to use Gauss's law to find that electric field. And Gauss's law is a law about closed surfaces. So Gauss's law says this: if I were to calculate the total flux through any closed surface, which is equal to the sum of all the EA cosine thetas across the entire surface, I'm going to get a value equal to 4 pi k times the charge inside the surface. And again, this is the algebraic form of Gauss's law. I'm going to go ahead and talk about the integral form of Gauss's law. In the language of integrals and vectors, the total flux through any surface is the integral over the entire surface. Oops, I'll get that centered. Of E dot dA. And that integral gives 4 pi k times the charge inside the surface. So whether you're using this algebraic form or the integral form really doesn't matter. I'm going to go ahead for the rest of this example talk about the integral form. All right. So now Gauss's law applies to closed surfaces. If I want to know the electric field at a point within this interior here, I need a surface that goes through that interior. Well, that's what this green circle that I've drawn is going to do for me. Okay, what I'm going to do here, normally if you were working this problem, you would just draw that surface and the interior. Just because of the way my program works, it was a little bit nicer for me to draw it out here and move it over there. So imagine now a surface, radius little r, right? And I'm going to go ahead and just center that right on the interior, right in the center of the sphere. And what I'm going to do is apply Gauss's law to the green surface. Now, there's some things that need to be understood. When you apply Gauss's law, one of the things you got to figure out, all right, is the charge inside the surface. Now, focus on my green surface. That's going to be my Gaussian surface. And notice that if I change its area, or I change its radius, if I make that surface bigger, there's more charge inside of it. Or if I make it smaller, there's less charge inside of it. So the charge inside of my Gaussian surface is a function of this r right there. So let me get rid of this stuff here. The charge inside that surface is a function of that little r there, the radius of the Gaussian surface. So that needs to be taken into account within this problem. So I'm going to go ahead and work this. So to work a Gauss's law problem, you draw your Gaussian surface. In this case, I did so in green. You try to mimic the surface you're working with. So because this is a spherical problem and I know it has spherical symmetry, I drew a spherical surface. Right? Then you write out Gauss's law, which has either this form algebraically or this form written as an integral. I'm going to go ahead and use the integral form here. Now, Gauss's law says integral E dot dA over the entire surface. And again, we're talking about the green surface. So what I always do here, I'm going to go ahead and I'm going to draw just a spot here, a little area. Okay, I'm going to go ahead and draw a dA vector at that point. So the dA vector, remember the dA vector is, oops, let me back up here, draw that a little shorter. Boom, there's my dA vector. And again, this thing has a magnitude of just dA, and it's in the direction of the normal. Now notice that anywhere I go on this green surface, the dA vector is going to be radially outward. All right, that's going to be an important fact for this problem. All right, now I'm going to draw an electric field vector at that point. I'm going to draw that in, let's draw that in red, I guess. All right, so if I draw an electric field vector at this point, now notice that if I'm right here on this surface, there's a bunch of charge over here with nothing to balance it out, so to speak, directly opposite. So from that observation, I know that the electric field vector is going to point something like this. Okay. Now, from the symmetry of the problem, it looks to me that the electric field vector is going to be perpendicular to, or I'm sorry, not perpendicular, but in exactly the same direction as the normal. And again, that just has to do with the symmetry of the problem. If I were to draw or look at an area somewhere else on this Gaussian surface, say right here, the normal vector would be this way, radially outward. The dA vector is in the same direction. Whoops, I should draw it the same length as I did before. Actually, back up and draw that normal a little bit smaller. Should draw it the same. Oops. Oh, I drew that in black. Okay, so let me go back here. I'm going to draw a dA vector, which is in the direction of the normal. Right. If I drew, I'm going to draw like one more, maybe like right here. So again, imagine that being a little spot on that sphere. I'm going to go ahead and draw the dA vector. Now, if you're using the algebraic form of this law, I would just draw normal vectors, all you have to draw. Right? Now, electric field vectors at all those different points. And again, by the symmetry of the problem, the electric field vector is going to be this way at this point. Right here, the electric field is going to be this way. The electric field should be radially outward at all points on that sphere. So I usually draw 3 or 4. You know, technically you can just draw one if you once you get good at using this law. But if you're having trouble getting it worked out, I would draw 3 or 4 different spots where you evaluate the electric field. And what you're doing is you're inspecting the relationship between the normal or the dA vector and the electric field. You'll notice that the angle between the dA and the electric field at this location is 0. At this location, 0. At this location, 0. In fact, at any location, as long as you are on the green surface, the Gaussian surface, the angle between the dA vector and the electric field will be 0. Right? Now, another important thing to take note of. Because of the symmetry of the problem, right? Here we're a distance little r away from the center, here little r, here little r. Looking at the symmetry of the problem, there's no reason for these electric fields to be different. So that means that the electric field is constant as far as the integral is concerned. The dot dA part, well, at every spot on that green surface, the angle between the dA and the electric field is 0. Cosine of 0 is 1. And therefore, what we end up with is the integral of just E times dA, because the E dot dA is magnitude of E, magnitude of dA, cosine of the angle between them. Cosine of the angle between them is 0. I'm sorry, cosine of 0 is 1, so E dot dA is just E times dA. Right? And again, I think what I'll do is I'm just going to keep going on the left-hand side, and then I'll talk about the right. Right, next step, so imagine we're moving around this green surface, and you got to imagine this, the mathematical process of integration. We're looking at the dA vector here, 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 here. The electric field's constant on the integral. It's not varying, so it can come out in front. And now the integral of dA, that just means add up all the little areas. If you add up all the little areas over the entire surface, you get the area of the surface. Keep in mind, though, it's the area of the green surface. So this is going to be 4 pi r squared. So the left-hand side of Gauss's law ends up being E times 4 pi r squared. I'm just going to take a moment here and talk about if you do the algebraic version here. Basically, same argument. If you look at just the normals everywhere rather than the dAs, here the cosine theta is between the normal and the electric field. Same argument, that angle right there is 0 everywhere, cosine of 0 is 1. This then reads sum of E times A. Keep it in mind that the electric field is constant over the sum, and you would end up right here, same spot, because you have the sum of all the little areas, which is going to give you the area of the green sphere. So that's how you go through and evaluate the left-hand side of Gauss's law for this problem. I'm going to go ahead and talk about the right-hand side now. 4 pi k q times the charge inside the surface. Actually, I'll just pull this down and just evaluate it here at the end. All right. So the charge inside the surface. Now, if you go back to the beginning of the video, remember that I could make that green surface bigger or smaller. An important thing to realize is if the green surface gets bigger, you have more charge inside the surface. In Gauss's law, this Q is the charge inside the surface. So that's this stuff inside of here. And it's important to note that it's a function of R. The bigger this green surface was, the more charge there was inside of it. Because this is a volume type of problem, this charge is spread out over a volume, I'm going to go ahead and calculate the volume charge density. So if you see my videos about charge density, this is rho. This is the charge per unit volume you can get by taking the total charge and divide by the total volume. The total volume of the cube, or I'm sorry, the total volume of the sphere is 4/3 pi r cubed. Important note, big R, because this charge Q is spread out over all of this. Oops. Total, we need the total radius. Okay. The charge inside of our surface we can get by taking the charge density, Q over 4/3 pi big R cubed, and multiplying it by the volume of our Gaussian surface, which is 4/3 pi little r cubed. So the charge density, so the charge inside the surface, let's see, the 4/3 goes away, the pi's go away. We end up with Q over big R cubed times little r cubed. So this expression gives the charge down within the green Gaussian surface at any value of R. Well, any value less than big R. And I'm just going to check some values, make sure it works. You notice if R is 0, I would get 0 out, means that if this thing were basically infinitely small, there'd be no charge inside of it. Notice if little r is equal to big R, the green surface would be right here at the outer red, the r's would cancel, and the charge inside is the total charge, big Q. So, I've found an expression for the charge inside the surface. I'm just going to put that over here. All right, 4 pi k times the charge inside the surface, which we just found. Okay. So now what I've done is I've evaluated both the left and right-hand side of Gauss's law. Now I'm just going to start simplifying things down here. Let's see, the 4 pi's go away. 2 of these little r's will cancel 2 of these and leave us with just 1 of them. So the electric field that we get, let's see, K big Q little r over big R cubed. And what we have now is the electric field as a function of the radius inside the spherical surface. I'm going to go ahead now and check it for some values. Remember at the very beginning of this, I took note that the electric field at the center should be 0. If you put R equals 0 in, we do in fact get a 0 out. It's dimensionally consistent, remember from other videos, that the electric field should always have units of kq over r squared, and it does. Now what I have right here is the magnitude of the electric field. If I want to turn that into electric field vector, let's see mathematically, here's how I can do that. I can say the electric field vector has a magnitude of kq over r cubed times little r. I'm separating these because these are constants within this problem. That's a variable. So constant times r. And then if I want to attach a direction, that direction would be just radially outward at all points, meaning like at this point it would be this way. At this point it would be this way. At this point it would be this way, and so forth. So what I can do is I could just define a unit vector for that. And that unit vector is in the direction of the radius. So I'm just going to put r hat here. So that means unit vector in the direction of r, and boom, there's my electric field vector for any points inside of the spherical surface. This result is not good outside the sphere, and the reason is because the charge inside the surface changes. It's no longer equal to this expression. Whoops. There we go. This expression, as long as the surface is outside. In fact, I'm going to go ahead and end this video, and I'm going to leave this as an exercise to the reader. If you go ahead and draw a new Gaussian surface outside of this, then the charge inside of that green Gaussian surface is equal to this. And your results should simplify to kq over little r squared pretty easily, but again, I'm going to leave that as an exercise to the reader. So the intention here was to give an example of how to use Gauss's law to, in a problem with spherical symmetry. I hope that this example helped, and hope everybody has a great day.